So thanks for being here tonight, and thank you for having me as part of the panel. So for decades, we've all been hearing about how our human-caused emissions are causing global warming. And with each new season, we're learning, sometimes painfully, what the consequences of that warming are. So for the next 15 minutes, I don't want to belabor the problem. We know the problem. I want to instead focus on the solutions. And very specifically, I want to focus on a solution that addresses the technical cause of climate change, the greenhouse gas emission. Okay, so for the next few moments, if you'll bear with me as I use a bathtub as an analogy for our atmosphere, as we discuss what we call our greenhouse gas budget. Now, briefly, a greenhouse gas is the molecule that gets released when we burn fossil fuels or when we change our patterns of land use. And when these molecules get in the air, they're really good at absorbing the heat that comes from the Earth's surface, and they like to radiate it in all directions, and one of those directions is back down. So essentially, they're acting as a blanket. So thousands of scientists have come together to decide how much of this greenhouse gas we can let flow into our bathtub before we start to overflow. And what I mean by overflow is uncontrolled warming. So in order to understand how to manage this budget, we have to understand what is causing. Where are all these greenhouse gases coming from? What are all those faucets draining or pouring into our bathtub? So the solution of how we manage this budget feels pretty obvious. We just got to turn off those faucets, right? We just have to turn them off. Well, before we do that, we have to appreciate, frankly, the diversity and the complexity of what all those sources of greenhouse gases are and where they're coming from around the world. Now, this slide is a very complex, cool plot. It's called a Sankey chart. This one was provided by the World Resource Institute. And the reason why I'm showing it here is not to lose you because you're trying to figure out what's going on. It's because I want you to appreciate the diversity and all the different kinds of emitters or faucets that we have that are leading to these greenhouse gas emissions. Some of these emitters we're all very aware of. That first picture is taken from Page. That's the old Navajo generating station that no longer is in the landscape, but our power sector is a major contributor. All of the things that are surrounding us, that we're sitting on, that we're wearing, that we're operating, those are materials that require heavy manufacturing. That is a major faucet that's filling up our bathtub. Our transportation sector, our agricultural practices, and even our wastes that get into the landfill. These are all those faucets. Now, if we turn these off right now completely, it's going to require massive social, economic, and technology transformations. And many times we know what we need to do, and those are economic solutions. We will go after them. But if we do all of it all at once, we may cause unjust harm, especially to populations that have hardly contributed to the problem in the first place. And now is just a really good time to remember that to date, the United States, the wealthiest nation in our world, has contributed the greatest cumulative amount of greenhouse gas emissions. And it's with that burden that we look forward to the solutions. So, it turns out, in addition to all of these faucets that's been filling our bathtub up with greenhouse gases, there's also quite a few drains that are available to us. One major drain, or sink, as the scientists call them, is our ocean. It has very slight alkalinity, and for years it's been slowly absorbing carbon dioxide, our most abundant greenhouse gas, because it's slightly acidic. Now, that is not a sink I am hoping to accelerate. But there's some others. The other obvious ones are our biosphere, so our forests and our wetlands. These are using natural photosynthetic processes that pull the carbon dioxide out of the air, trapping it as that biological hydrocarbon. There's also our geochemical cycles that I'll talk to in just a moment. So if we can't get those faucets off quickly and we can't turn them off completely, well, then we better start looking at what we can do to accelerate the sinks. And that is where I spend a lot of my energy. Now, thousands of scientists have come together to say, look, we have to start turning those faucets off now, and we have to start turning them down pretty fast, as evidenced by that red elbow in the curve there. That's what we need to do right now in order to limit the warming to only 2 degrees Celsius. Now that 2 degrees Celsius, or more aspirationally 1.5 degrees Celsius, this was the amount of warming that was decided upon in that Paris Accord Agreement back in 2015, that legally binding international treaty that's going to hopefully hold us accountable to how much greenhouse gas we put into our bathtub, the atmosphere. But nearly all scenarios know that just turning down those faucets is not going to be enough. We also have to get the greenhouse gas out of the atmosphere, and we have to start doing that by the end of the decade. And by the end of our century, we have to start doing that to the tune of 10 to 20 billion tons a year. Now, exactly where we land and how much we have to remove depends on how fast we can come off, how fast we can turn off those faucets, how fast we can come off our fossil fuels and our land use practices. Now, if we have to get that negative emission, if we have to accelerate the sinks, let's pay attention to what those sinks can be. So I already mentioned the natural biosphere. And as plants start to accumulate CO2 and building them into hydrocarbons, the living matter itself is a storage reservoir that will last for decades to hundreds of years if we can sustain that. As that material breaks down, it can be incorporated into our soils. Our soils can be a massive reservoir for all of that carbon. Our wetlands and coastal habitats are also really excellent reservoirs for that carbon dioxide, which is our most abundant greenhouse gas. The key there is we have to make sure that it's storing more than what it's already doing, and we're not reversing those changes, which means a lot of enforced land management policies for generations to ensure we have permanent storage. One other thing I just want to say about that sink is it'll do a lot for us, but it can only do so much because that land that stores that carbon is also providing another important activity, and that is providing us food and fiber. So we have to do more than just relying on those natural sinks. Another natural place for this carbon, and now I'm speaking very specifically about the most abundant greenhouse gas, so another obvious place for that carbon to go, carbon dioxide, is put it right back into the ground from which it came. And the reason why that's a good idea is because we know for millions of years, those porous volumes in rocks were trapping hydrocarbons, which was the original source of the carbon before we combusted it for our energy systems. Now we need to make sure that it gets down there far enough under several layers of dense rock. We want there to be tiny pores to trap it using a phenomena called capillary forces. And it's also really great if there's saline aquifers down there. Saline water is something that's not our drinking water, because that also will ensure it stays down there and stays there safely. But we certainly have to monitor it to make sure it's not interfering with anything else and it doesn't come up catastrophically. Now, the holy grail of storage is storing it as a solid. So allowing that slightly acidic greenhouse gas CO2 to react with our slightly alkaline minerals that are all over Earth's surface to form a carbonate rock. So I have a couple of props here today. This right here is trapped CO2 in the form of a mineral. I took this right off the NAU campus. This is our Kaibab limestone formation. You can also see this in the Grand Canyon. So this is a calcium magnesium carbonate rock that at one point in time reacted with CO2 and silicates. Also in Arizona, we have a whole bunch of these silicate minerals. So silicates tend to come from our volcanic geologic formations. This is taken from one of our young cinder cones in the region. And it happens, this particular sample that I'm showing you is in my lab because it has a lot of natural alkalinity in there. And so when I mean alkalinity, I'm really talking about magnesium and calcium in these materials. And the job of the engineer is to figure out how not to do this over millions of years, because that's not the rate that we're emitting. But we have to be able to accelerate this so we're hitting 10 to 20 billion tons a year. And so that's where I help think about the problem. What do we need to do to accelerate this process and get it into this state, which I haven't said already, is the thermodynamically most stable state for that carbon to exist in on the surface of our planet or near the surface of our planet. So what do we do to try to accelerate that sink? The first thing that's really helpful is if we can take that greenhouse gas, which is still very dilute in the atmosphere, roughly every 4 out of 10,000 molecules is a carbon dioxide molecule. And we want to be able to trap it. And the way we trap it is we put a material into the air. And so the materials I work with look no different than an index card. So I brought an index card tonight because we're treating them in the lab. I didn't want to bring them here. Looks no different than this, but it has a high affinity for the carbon dioxide. Why? Because it's alkaline. We're taking advantage of that high school chemistry acid-base process. So one of the tricks is, how do we do a good job of making sure we can pass all this air, pass these materials so it can trap sufficient amounts of carbon dioxide, and hopefully after it passes by, it's now less, it's even more dilute, which is our goal. We want less of it in the atmosphere. Now, the next step is, well, if I then took this material with all the carbon dioxide on it and I put that underground, that would be a problem because these are material inputs. And they cost something. And we want to make sure this is going to last for as long as possible. So we're going to want to cycle it. And to cycle it, there is the energy input. So we took advantage of some thermodynamic chemistry to get that CO2 trapped. We have to overcome that again to pull the carbon dioxide back off. All first-of-kind demonstrations that are already doing this take advantage of heat to remove the CO2, the carbon dioxide, from this material. Some of the first demonstrations needed really high temperature heat. That, of course, required a fossil fuel combustion. We want to move away from the combustion of fossil fuels. More recent materials are taking advantage of lower temperatures. That's handy because then we get to use renewably powered heat pumps to generate that heat, or maybe we have a waste heat stream, or maybe there's a nice geothermal source underground to help us out. But what I actually work on are materials that don't necessarily need heat to release that CO2. Here's a cartoon from a project that I'm on. We're actually taking a look at using moisture as our energy input. So when we hit these materials with water, this water vapor, which by the way is in the gas phase that we don't see, right guys, from the earlier trivia question. So when we hit this with water vapor, the CO2 likes to release. So one of the projects, I'm involved in several projects with these kinds of materials, is looking at, well, now water's our input, so how do we become as efficient as we can with that water? How do we best exploit this response? And how can we cycle the water using natural evaporation processes? Other colleagues around the world are looking at just simply applying an electric field to these materials to get that carbon dioxide to go. I'm looking at a combination of all of the above to try to get that CO2 to release, because the goal is we want it to be nice and concentrated. Once it's concentrated, it'll more quickly react with that solid mineral to get ourselves into the most stable state, which is as a carbonate rock. So other things that we need in order to get this thing to go quickly that we look towards is water. It's really good at trapping the high pressure CO2. It's also good at dissolving that rock. We also want surface area. So the figure on the slide is actually a core from a basalt deposit. So basalt is a form of silicate. This one's from Iceland. And those crystals that you're seeing there are the carbonate that's formed when it was injected underground. So they drilled that and pulled it back out of the ground to convince ourselves that, in fact, it did react to form the carbonate. But also what you'll see in that picture is there's a lot of pores in there. There's a lot of surface area. And that's indeed what we need to get the reaction. And so the silicate that I showed you just a minute ago, here taken from one of the Miller mine sites. So this is actually being quarried right now. We use this for the grit on our roads in the winter. When the roads get slippery, you can buy this at Landscape Connection. This material naturally comes to us pretty porous because of the way it was formed from those gaseous volcanic eruptions tens of thousands of years ago. So we look for surface area. You can get it by grinding and crushing. We're not really in the mood to do too much grinding and crushing because that is another energy input. Anything we do energetically hurts the negative emission. The other things I look at are catalysts. These are the ingredients that help accelerate the rates because, after all, that is what we're trying to do. So the good news is about all of this, because I know this is a fairly new field, is that there are several first-of-kind demonstrations already established in separating that carbon dioxide directly from the air. We call this direct air capture. Injecting that carbon dioxide now as a high-pressure supercritical fluid is what we call it. And we have evidence that these things are reacting pretty rapidly over several years. What I'm doing as an engineer is trying to find new materials that are more energy efficient, that are more affordable, and are faster, so we can get more of those negative emissions with the fewest amount of inputs necessary. And then finally, in wrapping up, I want to remind you that no one actually wants this bathtub to overflow. No one wants uncontrolled warming. So what we need to do is we need to turn off those faucets using the technology that we know is available and that is economic to use. And we also must accelerate the sinks. Thanks.
It's great. Thank you.
Yeah.
It's not easy to have a talk about climate change. A lot of times people are skeptical, or they've heard this before. But I love how you focus on, okay, yeah, climate change is here, but now we're focusing on what we can do to make things better. So my question is kind of similar. Mm-hmm. Now that my kids are a little bit older, and now they can at an age where they could understand global warming, how do we educate them on the problem without them becoming kind of apathetic? I want to be able to say, hey, it's a global problem. We all have to work together, but there's things that we can do that actually make things better ourselves.
Yeah. So I'm going to tell you there's days when I'm like, what did I actually accomplish today? Do we have that better material? Do I understand it a little bit more? And I can get really frustrated just in the act of science, right? We can get quite frustrated. So on those days, I remember that there's individual choices I have. And maybe that's my family deciding we're going to have a plant-based meal tonight. Or maybe that's deciding that I'm going to make my kids ride their bikes to school instead of idling my car in the bike lane. She's laughing because she knows I did that. But also, what I want to say is I'm just an engineer talking about how I approach the problem. We need more students going into science and engineering to help us with this problem, not just to accelerate the sinks, but also to transition our energy sectors over to renewably powered sectors and to improve our land use and agricultural practices. We need that capacity. But more than that, I remind you that it's more than engineers and scientists working on this problem. We were part of the problem. We weren't the whole problem. We're going to be part of the solution. We're not the whole solution. We need everyone to do all the things And we need all the disciplines to find their way to help contribute to this problem, even if it's the policy, legal teams, if it's the financing to figure out how we're going to funnel human wealth to solve this issue because it's not happening for free. Or even if it's just the artists and the communicators helping the world understand why. This is such a big problem. We need all hands on deck to help us in all the ways possible. The other thing I just want to say is we're going to try to do this with the least amount of impact as possible, trying our best not to make the big mistakes. We might make some mistakes, and people are going to keep watching us and holding us accountable to make sure we're learning and those mistakes stay small. But we should be supportive of all the kinds of solutions because we're going to need them all.
Excellent.
Yeah.
Thank you.
Thanks.